Welcome to this MOV on salts and buffered solutions. What happens to pH when ionic salts are added to water? Salt hydrolysis is this process where a dissociated cation or anion in aqueous solution may interact with water to either essentially add hydrogen ions forming an acidic solution or remove hydrogen ions forming a basic solution. So what are the acid-base properties of salts in aqueous solutions? We can have a neutral salt when a cation of a strong base and an anion of a strong acid are part of the salt. And so we need to know what our strong acids and bases are. So here's our list of strong acids that we just need to memorize. There's no other way about that. We just need to memorize what they are. And then our strong bases are a metal hydroxide. So sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, all of those. And one thing to consider is that these neutral salts are going to have a pH equal to 7. So neutral salts are going to have a pH that is equal to 7. That's why they're neutral. They're at a pH of 7. It's possible to see these cations or anions in combination with other cations and anions that are not neutral. And so that's what we see here. So we have an acidic salt, and so that's going to be a pH. pH is going to be less than 7. Okay. And that's going to contain a cation or a conjugate acid of a weak base, and of course a neutral anion, because that's going to make just that conjugate acid contribute to the pH. And then we can also have a basic salt, and that's going to contain the anion or the conjugate base of a weak acid and a neutral cation. And so that one's going to have a pH that's going to be greater than, pH is going to be greater than 7. Okay. And so we can kind of do some analysis and determine if a salt would be the result or would result in an acidic, a basic, or a neutral solution. So let's take a look at 3 examples here. So in the first one, when this would split apart in aqueous solution, we would split it apart into NH4 plus and Cl minus. And so the NH4 plus is actually the conjugate acid of ammonia, NH3, which is a weak base. On the other hand, chloride is the anion of HCl, which is a strong acid. So that makes the Cl neutral, okay? So that makes Cl is going to be neutral. But that NH4 is going to be acidic, okay? So it's the conjugate acid, so that makes this acidic, which makes our overall salt an acidic salt. So the next one that we're going to look at is sodium chloride, and we've already looked at chloride. Okay, so we said that chloride was the anion of a strong acid. So let's take a look at sodium. Sodium, Na plus, is going to be the cation of sodium hydroxide, which is a strong base. So that makes this sodium is going to be neutral. We know that chloride is also neutral, so that makes this salt a neutral salt. It is not going to impact pH. Finally, if we take a look at this last one, we already know that sodium is neutral. So then the question is what is the acetate? Okay, so the acetate is the C2H3O2 minus. Okay, and that is going to be the conjugate base or the anion, so conjugate base or anion of a weak acid, which would be acetic acid. So HC2H3O2 is a weak acid. So when this anion gets in there, it's going to interact with some hydrogens, removing them and acting as a base. And so that makes this one basic when it's added in solution. It'll cause a basic solution. Okay, so that leads us into buffers. So what are buffered solutions and how do they work? So a buffer is a solution that minimizes a change in pH. So if we add a strong acid or base to it, it's not going to change in pH as much. Now that happens within what we call buffering capacity, and that's the amount of hydrogen or hydroxide ions a buffer can absorb without a significant change in pH. And we have this equation that we use called the Henderson-Hasselbalch equation, and we use that to determine the pH of a buffered solution. This is the actual equation, and you'll notice that pKa shows up, and we've seen pKa once before. So this pKa that's here, we've seen that in a previous MOV where we looked at half equivalence point. And so pKa, just so we refresh our memory, is equal to the negative log of the Ka. And so we're going to use this to do some calculations. So how are these buffered solutions made? Well, buffers can be made for a specific pH, and so we'll use combinations of either a weak acid and its conjugate base, salt, or a weak base and its conjugate acid, salt, to be able to kind of rein in on a specific pH that we want to make a buffer for. So when we combine these, let's get an example of each. So if we want to have an acidic or a weak acid and its conjugate base, salt, then we would have for a weak acid something like acetic acid that we just saw, so HC2H3O2, that we would add in solution. And in addition to that, we would also have our salt that would have the anion, okay? So we would have something like sodium that we know is a neutral ion that would be in combination with the acetate, so C2H3O2. So when we would combine these two, we would get a buffered solution. In addition to that, we can have the weak base, okay? So a good example of a weak base is ammonia, NH3, and its conjugate acid is going to be NH4 plus, and we're going to add that in a salt, so something like ammonium chloride would be a good example. And so we would add these two together to be able to get a buffered solution. So we might also want to be able to determine the pH of a buffered solution, and so we can do some calculations with information. So if we know how much we add of the weak acid or the weak base and its conjugate salt, then we can determine that. And so we're going to use an ICE table for this. So ICE stands for initial change and at equilibrium. And then I go ahead and I just write out up top what I have for my equation for this weak acid and its conjugate base. And then we're going to plug in our initial concentrations. So we have an initial concentration of 0.5 molar nitrous acid, that's a weak acid, as opposed to nitric acid, that's a strong acid. So we have 0.50. we start off with no concentration of hydrogen, and then we have the 0.75 of KNO2, and that's where this NO2 is coming from. So the NO2 in here is coming from the potassium nitrite. All right, so then we're going to have a change. So we're going to say, all right, this one's going to change. We're going to actually push this in a net direction of to the right because we don't have any of that hydrogen. And so because of that, we're going to take away from the left side and we're going to add some amount to the right side until we establish equilibrium. So then at equilibrium, we're going to add these two up, and we're going to have 0.50 minus x. We're going to have x, and we're going to have 0.75 plus x. Now, an interesting thing when we go to solve these problems is that we have something called the 5% rule. And basically with the 5% rule, if we have an initial concentration, so if the K value is 10 to the negative second or less than that compared to the original concentration, then that amount is going to be insignificant when comparing them to those initial concentrations. And so in that case, we don't have to apply these x's. We can just use the concentrations. Okay. So now we're going to go ahead and plug these values in. So we see up top that Ka, and so we can write our Ka expression. There's two ways to solve this. I'm going to show you both. So Ka is equal to the concentration of hydrogen times the concentration of that nitrite ion divided by the concentration of the acid. Okay, so I'm going to plug those numbers in. So we have 4 times 10 to the negative fourth is equal to, on the other side we have x for our hydrogens. We're going to put that in there. So x times 0.75 divided by 0.50. Okay. And we want to solve for x. So in order to solve for x, we're going to do x is equal to 4 times 10 to the negative fourth times 0.50 divided by 0.75. Okay. And when I calculated that out, I got x is equal to 2.7 times 10 to the negative fourth. That is our concentration, so we'll say molar. That is equivalent to the concentration of hydrogen ions. And so if we want to know what the pH is going to be equal to the negative log of that value, 2.7 times 10 to the negative fourth. And that's going to give us a pH that is equal to 3.6. Okay, so that is our value for pH. Okay, so there's a second way to actually solve this same equation, and that is using the Henderson-Hasselbalch equation. So we're going to go ahead, and I've done up some of the work that we already had. So a second way to solve this is to actually use the Henderson-Hasselbalch equation. So what I wanted to do is get what my pKa is. So here I went ahead and solved for pKa, which was 3.4. Okay. And then I'm going to plug that into the Henderson-Hasselbalch equation. So to find pH, we're going to take that 3.4 that we have from up here, and we're going to add that to the log of the anion over the weak acid. And so in that case, we have 0.75 0.75 divided by 0.50. Okay, so pH in this case is going to be equal to 3.4 plus, and when I took the log of this value already, I got 0.2, and so when I add those up, our pH is equal to 3.6. And so you'll notice that we use two different methods to do the same thing and get the same value for pH. So those are two different possible ways that you can do that. Okay, so the next one is we want to find out how much the pH of a solution will change if we add a strong base to the solution. And in the first one, we're going to add it to water. Okay, and so remember that water is neutral. Okay, so water, distilled water, is going to be neutral with a pH equal to 7. And so in order to do this, we just basically need to find out what happens. So we have that our KOH in water is going to split apart into a K plus an OH minus, and it's a 1-to-1 ratio. So that means that the concentration of hydroxide is going to be equal to 0.25 moles. Okay, so if we have 0.25 moles of KOH, then we're going to have 0.25 moles of hydroxide. So now our POH can be calculated, and that's going to be the negative log of the concentration of OH minus, which is going to be the negative log of 0.25. And when we calculate that out, we get 0.60. Now that's POH, that's not pH, so now we have to apply that to find pH. So pH is equal to 14 minus the POH, which is 0.60. And that gives us a value of 13.4, okay? So if we go back and we look at this, if we say, well, our neutral solution was a pH of 7, so the change in pH is going to be the difference between 13.4 and 7. And so that's a change in pH of 6.4, which is a pretty large amount of change. Okay. So how does that compare to if we added the same amount of KOH, of this strong base, to a buffered solution? So that's what we're going to take a look at next. So what is the pH of a buffered solution with the nitrous acid that we originally had, and the potassium nitrite that we originally had, if we have 0.25 moles of KOH that's added to it? So we're going to take some of those values that we had earlier, okay, and we're going to use the Henderson-Hasselbalch equation for this. Oops, sorry, put that back up. Okay, so in this case, we already established that the 5% rule did work for us, so we're going to still use that 5% rule. And we're going to plug in those values that we had. And so we said that we started off with 0.50, okay? And in this case, that KOH value that we have, that 0.25 moles of KOH, is going to go right here. Okay. And then we are going to have the original amount that we had for our nitrite, which was 0.75. And actually, we don't even have to worry about the 5% rule here because we're just going to use these values in order to find out what happens. So when we add this, when we add these two together, so when we're adding more of this, we're going to push this in this direction, to the right, and establish more of the nitrite anion. And so that means that we are going to subtract from the left side 0.25, and we're going to add that to the right side, 0.25. Okay? And it depends upon whether you're adding a strong acid or a strong base in which direction you end up going. So you may have questions about that later. So that means at equilibrium, when we add these all up, we're going to get some values. We're going to add those, and we get 0.25, we get 0, and we get 0.50. Oh, excuse me, I'm adding it on that side. I always make that mistake. We want to make that 1.0. Okay. So now we're going to plug these values in. Okay. So these two values are going to get plugged into the equation in these locations. So we are going to put those up here into the Henderson-Hasselbalch equation. We already know that our pKa from previous was 3.4. Okay. So this was 3.4 from before when we calculated that out. So let's go ahead and plug these in. So pH is equal to 3.4 plus the log of 1.0 on the top divided by 0.25 on the bottom. Okay. And so when I calculated that out, I get 3.4 plus 0.6, which is 4.0. Now our original pH, if we want to know the change in pH from our previous buffered solution problem, was that we had 3.6, and so the change from 4.0 to 3.6 is going to be a difference of 0.4. That's a lot smaller amount of difference compared to the change without a buffer. So we will work on some additional problems in class, and I hope that helps to get you started.